we'll go back to Albert's special relativity. This is just to give you a little context of some stuff I'm going to talk about for the rest of this chapter. Could you sit a little bit over because I'm trying to videotape it, and your bag is probably blocking the bottom of our screen. It's okay, no problem. Normally it doesn't be the case, but since there's so many people graduating in theory, our friends are graduating. Okay, so I don't know how many of you know much about Albert, but Albert, he was a Bern patent clerk. That was his sort of side job. He studied physics in the university, but didn't get so far, and he got this great job as a Burton patent clerk. Basically, he had a lot of free time in his job, and in his free time, he came up with these three extremely important papers in his Annus Mirabilis, as I've called it before, and this was one of those papers, the Special Theory of Relativity in 1905. Essentially, he fixed several shortcomings for objects moving near the speed of light that Newton's equations could not solve. People already could see there were shortcomings in Newton's equations for these objects traveling near the speed of light. And in essence, what it amounts to is that time moves more slowly for objects with velocities approaching the speed of light. Could you move just a couple of chairs just that direction? That's something we call time dilation. So this was observed. Also, objects moving near the speed of light also appear to be shorter for an outside observer. I don't expect you to know these equations, but I want you to know that that's what happens. So there's a time dilation effect. If you're traveling super fast at the speed of light, time, you don't perceive it, but time does move more slowly for you. So if I left here today and I went to Alpha Centauri 4 light years away and I traveled at almost the speed of light, you can't really travel the speed of light if you're a massive particle because it takes an infinite amount of force. But let's just say that I travel near the speed of light, I shoot off there, that's 4 light years away. Okay, it should be 4 years, and then I come back, another 4 years. So when I come back after going to Alpha Centauri, 8 years should have passed for me on this journey, you would think. Certainly when I get back to Earth, 8 years will have passed here on Earth. But for me, since I'm traveling so close to the speed of light, basically time for me slows down almost to a standstill from an outside observer. So I'll come back 8 years later and I won't have aged more than a day or something like that. Okay, that's what his theory predicts, and it has been proven experimentally that this is the case. As I mentioned before, what they've done is they've flown atomic clocks, which are the most precise clocks you can build, and they put those on planes, and they've flown these planes around the Earth a couple times at speeds, of course, much less than the speed of light, but nonetheless at some velocity, and they can make this calculation, and they can see that time did pass a bit more slowly on those planes. So not only are they having class or this commencement today, but they're drilling in the building apparently. I guess they don't want us to meet on Thursdays. Another consequence of that, as I just said, is this Lorentz contraction. Lorentz predicted this before Albert came along. There's a contraction also. So if you're in a really long spaceship, as you move towards the speed of light, it will appear to outside observer that your spaceship shrinks in size. But for you, being on the spaceship, you don't perceive this. Okay, that's some of the predictions of Albert's special theory of relativity. That was in chapter S2. I didn't expect you to read that, but I just want you to keep those sort of things in mind. Some other special essential points of this theory are that all motion or velocity is relative, hence the word relative, special relativity. The laws of the nature are the same for everyone, everywhere in the universe. It's another thing that his theory predicts. No matter where I am, the laws will be the same, and those equations help make it so. The speed of light is the same for everyone, everywhere in the universe. So no matter if I'm traveling 99% near the speed of light, the laws, I will still perceive light being beamed from me, traveling at the speed of light. And of course, as we've already talked, energy and matter are indistinguishable. That E equals mc squared that we talked about much earlier in the course. Okay, so those are the essential points of Albert's 1905 theory of special relativity. But then, 10 years later, he publishes something he calls general relativity, described as, say, a geometrical theory of gravitation that uses mathematics that we call differential geometry. So if you want to work in general relativity, you have to learn a little branch of mathematics to process those equations nicely. It includes solutions for accelerated motion, not just velocity. So the special theory of relativity was only for objects traveling at a fixed velocity. It did not work for accelerated objects. This really unifies special relativity and Newton's law of universal gravitation, which we talked about earlier. And, as we discussed in that previous class, showed that gravitational acceleration can be described by the curvature of space and time, this space-time business. Okay, so again, there's nothing really to memorize per se, but that's just the general concepts behind the special theory. And that's again in chapter S3. If you really feel inspired after this class is over, go to chapters S2 and S3 and work some problems for fun. Actually, the special theory of relativity is very easy to calculate a few things, and you can just get a feel for how time works and then those kind of things. Okay. So the reason I had to talk a little bit about at least the special theory of relativity is because I want to talk about what happens to you as you fall into a black hole. We've got so many questions about black holes, I figured everybody likes to learn about black holes, so we'll talk a little bit more about them. So the idea is, as a fellow astronaut falls in, what will you see as an observer outside of that frame of reference for him? Okay, so I'm very far away from the black hole. The black hole's down there. And this guy, this fellow astronaut, gets out of the ship and goes, I want to go check out this black hole. I don't believe these theories. I want to go see if it really is a wormhole. I'm going to go for it. So you stand outside, you say, okay, man, go for it. The first thing you see is that there'll be a gravitational redshift. So the photons that are emitted from his spaceship, say his spaceship normally emits photons with, say, yellow light, for example. But as he moves towards this black hole, he'll be accelerating at a high rate, and those photons will be redshifted. They'll be Doppler shifted to the red. So he'll be accelerating very fast away from me, and I will see that as a redshift. Okay. Another thing is that time will slow down as the force of gravity increases. Again, it gets closer and closer, the force of gravity gets higher and higher, and the speed is increasing more and more. And I told you, as you get near the speed of light, time slows down for you. So for him, he sees things as normal, but for me, I can see. I'll see a clock from his spaceship, and I'll see his clock slowing down in time. He's going to broadcast that clock to me. Time will completely stop once he reaches the event horizon of the black hole. And he'll just stop there. And he'll be frozen there forever from my viewpoint. He didn't know that before he decided to go check it out. What does he see? The guy or her who falls into the black hole. First, they see my gravitational blue shift. They see it the opposite. They don't see a red shift. They see that photons coming from me are blue shifted. They'll see time increasing in speed from me, because I'll have a clock too. My clock will seem to be speeding up. His time, as I said, will be ticking away like normal. He'll perceive that his clock is working just fine, no problem. And he'll see himself across the event horizon. So here's a little picture. Let's see if this decides to work. Yes. There we go. So here's that picture. There's the event horizon. And two spaceships. And one is going to start to fall towards this black hole. There he goes. He slows down. Starts falling in. We're just going to miss each other there. And you can see he starts to turn red. And his clock is slowing down. I'm at 2 minutes. He's at 1:33. Slowing down a little more. You can see that. And then, boom. That's how I see it. So, 1:38, he hits the event horizon and he freezes. And that's after 3 minutes for me. So that's a consequence of this relativity equation. So, could I get you to just move over 2 seats, please? I know. I'll explain why. All right, so. So now I want to talk about another cosmological event of interest, and these are called gamma ray bursts. Why are they interesting? Because they're the largest bursts of energy in the universe, and they manifest themselves as gamma rays. First discovered in the late 1960s by US military satellites. This was a Vela program. They basically had launched these satellites up into orbit looking for gamma rays from Earth. They were pointed down at Earth because one of the byproducts of a nuclear test explosion are gamma rays. So it was a way to verify testing bans or to see if the Soviets were testing new nuclear weapons. But they sent these things up there and they started detecting gamma rays. But the gamma rays weren't down here, they were behind them. So they were quite confused at first about that. Finally, it wasn't until 1973 that that information was declassified. And also the GRBs were seen because there was a gamma ray detector on both the Apollo and the Soviet. The Apollo program was the American program that went to the moon, and the Soviet Venera probes, those are the probes that went to Venus. They both had gamma ray detectors, and they both also had detected these gamma ray bursts. They didn't know exactly where they were coming from, but they knew that they were not coming from Earth. Okay, so for a long time there were two competing schools of thought on what these gamma ray bursts were and where they were located. One guy thought that they were located in our galaxy. There was some consequence of events in our galaxy, maybe some kind of exploding object in our galaxy. Another guy thought they were of extragalactic origin. Bohdan Brzezinski, he was my neighbor when I worked at Princeton many years ago. So Bohdan said, I think they're extragalactic, and he thought he had some good reasons for believing that. It wasn't until 1991 that NASA launched the first serious gamma ray observatory that wasn't controlled by the military anyway. And they found that the bursts were evenly distributed around the sky. And that immediately told everybody that those were extragalactic, they were of extragalactic origin, because if they had been native to the Milky Way, they would have probably mostly been located in the disk of the Milky Way. We would have seen a distribution of these gamma ray bursts would have been in a plane, mostly along the Milky Way plane in the sky. But they weren't. They were in all different areas of the sky. And again, after several years of quick follow-up observations, so basically one of these things would go off, and they would tell a whole bunch of volunteer astronomers or observatories, go check out this thing. Let's go see if we can find out where it is. And they eventually realized that these things were actually co-located in external galaxies. Okay, they're really observed to the farthest reaches of the universe. That's what makes them interesting. What's even more interesting is if these bursts, as we measure them, were to emit their energy in all directions, and we're just seeing one little piece of that, they would emit so much luminosity that they would outshine the Milky Way and its entirety by 1,000,000 times. That's how bright these are scary objects. If one of these things, if this is true and one of these things went off in our neighborhood, we'd be finished.
How many times?
1,000,000 times the entire luminous output of the Milky Way. Okay? The Milky Way is an object with billions of stars. So you're talking about a lot of energy. But we don't actually think that they emit like that. We think that the energy is beamed, that they kind of explode in a cone like this, in essence, and that we're just looking down one of those beams. If that's the case, well, then it's only about 1,000 times the entire luminosity of the Milky Way when they blow up. Still, a pretty big explosion. Okay, only 1,000 versus 1,000,000, but incredible. It turns out that there are two classes of these gigantic explosions, long and short bursts. That means they're just brighter for longer or shorter periods of time, and we're going to talk a little bit about those. So we think from what we know about simulations, theory, and observations that the long bursts are likely to be created from super powerful supernovae that have created a black hole instead of a neutron star, and these are called hypernovae. Sit all the way over or this That's the reason we know that is because we found several of these associated with optical supernovae. Remember, these are detected by gamma ray detectors, but people have done very quick follow-up observations. There's a satellite called SWIFT, whose whole job is to swiftly find out where on the sky this gamma ray burst occurs. And the first thing it does is it sends those coordinates to a selection of ground-based observatories, and their job is to immediately point a telescope at these things and find out where they are and how far away they are. So again, they found that these long bursts are associated with supernovae. The short bursts, we believe, are due to the merger of either a neutron-neutron star pair or a black hole, not a black hole, little typo there, neutron star pair. And these are found in what appear to be near star-forming regions. That wouldn't surprise you, because you know that these supermassive stars, they don't live very long, and some of them might not be completely out of the star-forming region yet before they blow up. Okay, so if it's a short burst from these neutron-neutron star black hole mergers, then we should detect large gravitational waves prior to that burst as they're infalling. That's a prediction from Einstein's theory of relativity, that there should be gravitational waves associated with these kind of massive objects, and they should be the easiest type of gravitational wave to detect today. We actually have gravitational wave observatories on Earth. I won't have that much time to talk about them, but one of them is called LIGO, Light Interferometry Gravitational Observatory, I think that's what it is. And the other one that they want to build is a space antenna. Light Interferometry Space Antenna, I think it's called. So this one's operating, LIGO. I think there are 3 sites in the world, or 4 sites. There's 2 in the United States, there's 1 in Europe, and I think there's 1 now in Japan. And they're looking for gravitational waves. They haven't found any yet, because it's very noisy. The Earth is a big noise source for them. They're detecting very, very small fluctuations on the order the size of an atom's orbit. So at those kind of scales or less. Anyway, if these things go off, this observatory should be able to detect them with some luck. How do we know that? Well, we've done these simulations. So here's a little simulation. Okay, of course, the computer doesn't like me. Let's try to do it quite literally. Let's try. Sorry, wrong chapter. Chapter 18. Neutron star collision. Here it is. Let's see if it plays. Oh, that's what it looks like. So this is a real simulation that's been done to see what happens when these neutron stars collide. I'll show you one that's a bit more sophisticated and more recent. This is a couple years old. And those neutron stars eventually join each other and then produce all kinds of gravitational waves that in theory these observatories would detect if they're sensitive. Okay, that's one. I'll show you another one, too. Let's see if this one is more friendly. Nope. Try this one. Okay. So this next one is a black hole merger. That's another possibility. This is done by a colleague of mine at Goddard Space Flight Center. She gave a talk last year at Columbia University, and I asked her for a copy of her simulation. So this is the simulation of these 2 black holes merging, and you can see the magnetic field lines and the gravitational field lines around these black holes. So let's see if they're going to be friendly or no, of course not. Okay, well let me try again. Yep, there it is. So there they are. Here's the black holes. This is a real simulation. This is done on a monster supercomputer. Here they're zooming out so you can see the gravitational waves and some magnetic field lines. And then they're going to spiral in. And as they get closer and closer, they generate more and more of these gravitational waves. and then that's it, they're finished. And then you have a little merged black hole there. Of course it'd be black. You wouldn't see it, but that's the simulation. So again, we have pretty good evidence. A friend of mine at NYU, he models those hypernovas I talked about before, also using kind of a little supercomputer they have down there to figure out how these hypernovae can explode and then have these kind of jets that go along with them, and how you can get the right energies that you're measuring here on Earth from those jet-like explosions. Okay. Okay, so yeah, let's move on then to chapter 20. I thought that was the last slide. Okay, so now we're going to talk about galaxies and cosmology. We're going to talk about cosmology for these next two chapters. Yes, ma'am.
The evaporation process of a black hole starts after.
The evaporation process could happen before they merge, after they merge. It doesn't matter whether they're merging or not. The evaporation process goes on anyway. But again, that evaporation process is an extremely slow process, right, as I told you. It's not like they're going to evaporate in a couple of years. They're going to evaporate in long, long periods of time, especially something that's millions of solar masses, for example, like the one in our center of our solar system.
Longer than the type, the brother stars.
Oh, much longer, much longer. Billions of years. Billions of years. Okay, so we'll talk about galaxies and cosmology, and I go back, now we're going all the way back to the beginning of the course, where we talked about these different, our cosmic address and how we fit into the cosmos, Earth, inside of the solar system, inside of our Milky Way. Remember, we're not the center of our Milky Way. Our local group of galaxies and the local supercluster, and then part of that whole universe. So hopefully you'll have a little better understanding by this course about all of this stuff. So in the beginning I talked about how many galaxies we have in the universe. We get some estimates of that from galaxy counts from these Hubble Deep Field and Hubble Ultra Deep Field observations that were made. The Hubble Deep Field was a 10-day exposure and a relatively empty part of the sky. So they kept the telescope focused in the equivalent of 10 full days, 10 times 24 hours, looking in the same part of the sky with that telescope, just sitting there, looking at it, integrating. Yes, sir?
In order to for a 10 exposure, it would have to tilt very, very slowly to compensate for.
Oh yeah, the Hubble Space Telescope is completely steerable. Yes, it has gyroscopes in it. It can look at any region of the sky all the time. The biggest problem for the Hubble is to stay away from looking at the sun, so it doesn't destroy all of its instruments. So there's very sophisticated programming involved in the Hubble to make sure it doesn't point the wrong way and die. Okay, good question. Okay, so even our deepest images of the universe from these two images show a huge variety of galaxies, billions of light years away. And we're seeing them as they were formed billions of years ago. It took that light billions of years to get here, so we're seeing those galaxies when they were extremely young, just born. Maybe when the universe is only 1 billion years old, or something like that. But even those galaxies, we see a great deal of diversity, just like we see in the local universe. This is just a picture of, well, I believe it's not very good, but I won't show that so much. But the reason we're interested in it is there's a very good relationship between a galaxy's age, its distance from us, and the age of our universe. And we're going to talk about all of those. So in order to understand all of these, we have to understand each of them together. So we have to consider the evolution of our universe and understand the evolution of galaxies also, because galaxies will evolve over the age of our universe, of course, in different ways. So, of course, we're going to categorize these galaxies, so there's all different kinds. We're going to try to figure out how distances to galaxies are measured. We can get distances to galaxies. And we're going to learn how those distances led us to measure the expansion of the universe and some consequences for galaxy evolution. That's what we hope to get to by the end of this lecture. So the three main types of galaxies: spiral galaxy, just like our Milky Way is a spiral galaxy with a disk. I'll go into some more details about that, but a lot of young stars, cold gas and dust, of course, like those pillars of creation I showed you yesterday, creating young stars, and then a bulge and halo population of older stars. I'll show you some of that. Elliptical galaxies. These are ellipsoidal in shape, like a football, you could think about it that way, or even circular, like a sphere. Not too much gas or dust for star formation in those. They don't seem to have a lot of star formation, or very little. And then these things we call irregular galaxies. So basically we can't categorize them as spiral or elliptical because they just look a bit strange. And I'll show you some pictures of those. And those come in all kinds of types. Of course, galaxies come in a whole range of sizes too. You have these dwarf galaxies, like the large and small Magellan Clouds, our closest galaxy neighbors, maybe only have a few 100 million stars. And then you have these giant galaxies, often found at the centers of these tremendously large galaxy clusters. A galaxy cluster might have thousands of galaxies gravitationally bound to each other. But this central galaxy, which are often called CD galaxies, they can have up to 1 trillion stars or more in that galaxy. That's because we believe those galaxies have actually cannibalized some other galaxies, and they've kind of grown from this cannibalization process. That's one theory. Okay, so here's a picture of that Hubble Deep Field. And even in the Hubble Deep Field, again, this very, very early image of the galaxy, we can find spiral galaxies. You can find elliptical galaxies. You can find strange, irregular galaxies. They don't look anything like you would expect a galaxy to look like. Okay, so let's talk about each of these in turn. So again, spiral galaxies have two components, essentially. They have a disk component and they have spheroidal components, we call them. So that disk component you're very familiar with by now. It's a flat disk. The stars follow nearly circular orbits, slightly elliptical, of course. That disk contains stars of all ages and types. We call them population 1 and population 2. That just basically tells you whether it's a recently formed star or if it's an older star. And of course, as we've said before, it contains an interstellar medium of cold gas and dust that will help us keep stars forming in that disk. Then that spheroidal component, we call it, has two pieces. It has a bulge and a halo. The stellar orbits are of random inclination and ellipticity, and they don't have too much cold gas in this. There's not much star formation going on in the bulge of our galaxy or in the halo of our galaxy. So this is what a typical spiral galaxy, this is what our galaxy would look like from the outside, roughly. So you have this kind of disk, you have a plane here, you have the bulge component in the center, and then you have this kind of diffuse halo. I drew a little picture on the blackboard the other day, also what that kind of looks like. So here's another picture. Again, here you have a disk with a lot of gas and dust, so it's opaque to visible light, but if I was looking at this galaxy in the infrared, I could probably see through a lot of that disk, especially looking in the far infrared. And again, has a very large spheroidal component with the bulge, and then of course a halo of stars, which are harder to see. But again, you see most of the gas and dust is all in this disk. You don't see too much of that kind of stuff outside of the disk. Here's another one, again, a disk component. These are spiral arms. These spiral arms are, we believe, pressure density waves, where there's an increase in density there, and that's where the stars start to form, because you're able to compress the clouds, and you get star formation pretty well. So that's where all the young stars are. Here's some old stars in the bulge, and then there'll be a halo of stars of much lower density around it. And there's what the orbits would look like. So here's what the disk would look like. Again, they wobble a little bit, but more or less circular. And then those spheroidal components will come in all different kinds of inclinations. Okay, of course, the disk and bulge propulsions can vary. If you didn't already guess that, this is a famous galaxy, the Sombrero Galaxy. I just showed you that a minute ago. Bars are often found in these galaxies. And there are people, again, a few people who spend their entire lives trying to figure out how these galaxies can form bars, how long the bars last, things of this nature. Then there's some without any spiral arms at all. They call them lenticulars. So here you have kind of density waves or whatever, but you don't have spiral arms, or you have something like this that has kind of a bar, but no spiral arms. They're very, very different kinds of spiral galaxies. Okay, then we have these other kinds of galaxies, these elliptical galaxies. They're not quite as varied as the spiral galaxies. Basically, there's either no disk or it has a very, very tiny disk at the center, which is hard to discern. They really just look like the bulge component and halo component of a spiral galaxy. So you can almost think about them as a spiral galaxy without a disk. This is an example of one, M87. That's a pretty close galaxy to us. And again, orbits for these objects are going in all kinds of different directions, all different inclinations, highly elliptical, some circular, etc., etc. Here's another one, M105, another elliptical galaxy. I'm trying to block my camera. Oh, thank you. Again, these elliptical galaxies don't have very much cool gas and dust, so they don't have much star formation going on in them. They look yellow or red in color. Very few blue stars, again an indication that there's not a lot of star formation going on. I told you, young stars tend to emit most of their radiation in the blue or ultraviolet. Older stars do not. Some of these have large amounts of hot X-ray emitting gas in them, for various reasons we won't have time to go into, unfortunately. And there are even small ellipticals with even less than 1 billion stars, and these appear to be the most common type of galaxy in the universe. Just looking at galaxy counts, these kind of small elliptical galaxies. Then there are these irregular galaxies. So here's a picture of a really weird-looking irregular galaxy. This is one of the Magellan Clouds. So these are basically, as I said, galaxies that don't fit into those other two classes. They come in all kinds of shapes and sizes. They often, I say often, not every time, contain some cool gas and dust. Often have newly formed young stars in them. Most tend to be smaller in size than Milky Way galaxies. And our observations tell us that there were more of these in the early universe than there are today. A lot of people think these are the results of collisions between small little dwarf galaxies. So again, here's a large Magellan Cloud. Here's a little one called M82, the cigar galaxy. People love to give strange names to these things. Okay. But, of course, some people have tried to come up with systematic ways to classify galaxies. And it started back in the 20s with this guy, Edwin Hubble, who the Hubble Space Telescope was named after, and a Swedish scientist named Knut Lundmark. Each of them, we believe separately, came up with a classification scheme that they thought would yield some insights into how these galaxies form and how they evolve over time. But in fact, the classification schemes didn't turn out to be so useful after all, and other people came up with different kinds of classification schemes. But, well, it's nice to classify things, but maybe it's not that useful per se. But this is what Hubble's classification scheme looked like. He put disk-dominated type galaxies on the right and spheroidal components on the left, and he ranked these spheroidal parts from 0 to 5, depending on how round they were versus being more cigar-shaped per se. And then there were some intermediate class objects called S0s, which were kind of between elliptical galaxies and spirals. And then he, again, ranked them based on larger bulge, less dusty gas, lighter spiral arms. You can see that that's what's going on. Here you have barred spiral galaxies, and here you have normal spiral galaxies. So that was the kind of classification that came up with. So we need to talk a little bit about how galaxies are also grouped together. So spiral galaxies are often found in small groups of galaxies up to a few dozen, or they're found relatively isolated in the universe. So they don't like to hang around big agglomerations of galaxies. Elliptical galaxies, on the other hand, love to hang out in these incredibly dense clusters of galaxies. This is a picture from the Hubble Space Telescope. This is kind of one of these famous pictures. I should have kept the caption on it, but I don't have it. Because this one has a lot of gravitational lenses. You can see them here. These are background galaxies whose light is being distorted by the intense gravitational field of this galaxy cluster. And actually they can now use these these gravitational lenses to figure out what the total mass of these galaxy clusters are. But nonetheless, you mostly find spiral galaxies, especially in the core, elliptical galaxies, especially in the cores of these giant clusters of galaxies. You might find spiral galaxies at the outskirts, maybe getting ready to fall in, but they soon lose their gas as they travel into that galaxy cluster. Okay, so in order to find out what's going on with these galaxies at all these different times in the universe, from today to, say, when the universe was only 1 billion years ago, we have to get their distances, right? And then, of course, that means that would give us their intrinsic luminosity, so we could see if galaxies have some luminosity evolution over their lifetimes, which could be quite interesting to figure out what happens to these galaxies over billions and billions of years. And it probably can also tell us about, as we'll see, the size, age, and density of our universe. We can get a handle on these distances. So let's talk a little bit about how we actually get distances to galaxies. It's all built up one by one to get these distances. We start out with, well, I'll talk about these in a little detail, but radar ranging to figure out the distance of our orbit around the sun. Parallax measurements, which you're extremely familiar with now. Main sequence fitting, we'll talk a little bit about that. Cepheid variables, which I touched on a little bit, and then some other distance standards. Things like white dwarf supernovae we talked about yesterday, and this is called the Fisher relation. And then we'll also talk about how we can use something called the Hubble constant. Okay, so the first thing we have to figure out, if we want to measure distances to the local universe, we want to do parallax measurements, we've got to figure out what our baseline is, right? We've got to figure out what an AU is. Okay, nowadays that's done from radar ranging measurements to Venus. Remember, I showed you how you can use Kepler's laws to get the distances to all the different planets in the solar system, basically. But to get the actual distance to the sun, you've got to measure the exact distance from Earth to one of these planets to plug into the equations. And that's now done with radar ranging. But if you remember, I talked a couple lectures ago about the initial estimate, which was done to figure out the distance of Earth to Venus. That was done by a Venus transit on the surface of the sun using parallax measurements from Earth. So two people on either side of the Earth, they measured where Venus was with respect to the sun as it was crossing, and then they could figure out what that angle was, essentially, and then figure out how far away it was, using a parallax based on Earth's own baseline to figure out exactly how far away Venus was. So instead of doing that today, we can just use radar. We bounce radar waves off the top of Venus's atmosphere, and we can figure out the travel time, traveling at the speed of light, of course, and then figure out how far away it is exactly. Okay, so once we can figure out exactly what an AU is, which we do this way, we can use parallax measurements to nearby stars. We've already talked about this a bit yesterday. Once I get the parallax distances to nearby stars, I can start to give these stars specific luminosities. I can figure out what kind of luminosity, intrinsic luminosity a star has. If I can figure out the star's distance, of course, I can figure out what its intrinsic luminosity is given its apparent brightness. I showed you this equation yesterday. That's just the inverse square law. Or, as we discussed, if I can figure out what the object's intrinsic luminosity is through some other means, and I know its apparent brightness, I can figure out its distance. And we'll see that this is extremely important because there are objects, without knowing their exact distances, we can figure out what their intrinsic luminosities are. And those objects, we call them standard candles. So we can figure out what the object's intrinsic luminosity is, I can measure its apparent brightness, and then figure out how far away it is. We'll find out that things like white dwarf supernovae and Cepheids fall into that category. Okay, so I don't think I have to do this. I did this last time, but there's some examples in how to calculate these things, calculating the distance based on the intrinsic luminosity and the apparent brightness. I showed you how to do that yesterday, so I don't think there's any reason to go through it again. But make sure you know how to do this. It's highly recommended. Okay. So, we talked about AU, parallax, and now we'll look at these standard candles. And there are several methods in use today to get the intrinsic luminosities of objects, and we're going to talk a little bit about each of them. Main sequence splitting, Cepheids, white dwarf supernovae, something called the Tully-Fisher relation, and then we'll finally get down to Hubble's law, which is not a standard candle method, but it's another way to get distances to really, really far, really, really distant objects in the universe. Okay, first, main sequence fitting. So we try to use stars brighter than G2 stars, stars roughly brighter than what our star is, that sit on that main sequence of the HR diagram, which I told you that you should be dreaming about by now. We find this open cluster close enough for parallax measurements so that we can figure out exactly how far the stars are. I plot them on an HR diagram, and I use the inverse square law to figure out exactly what their intrinsic luminosities are from their apparent brightnesses. So I can figure out for a given cluster what the intrinsic luminosities of the stars are in that cluster. Then I look at stars in another cluster too far away for parallax. Again, I measure their apparent brightness. I assume that they have the same kinds of main sequence stars, and that those main sequence stars have the same kinds of intrinsic luminosities as the one I looked at before, so I can get those stars' intrinsic luminosities, and using that I can use, again, the inverse square law. So I use their apparent brightness, what I assume to be their intrinsic luminosities, to get the distance to that open cluster, for example. But this is really only useful for distances within the Milky Way, because I have to resolve each of those stars in that open cluster. So this is kind of what it looks like. I don't expect you to calculate anything that you see here. I just want you to know a little bit how this method works. So don't worry about the math so much, but just think about the concept involved. So here you have the inverse square law and the same intrinsic luminosity. So if I solve these and I set L1 equal to L2, here's just our distance equation. Here's the apparent brightness for one cluster, its intrinsic luminosity, and its distance. And I divide that by the other one, so I get a ratio of those brightnesses. And I know that their intrinsic luminosity is the same. I can solve each of these in terms of the other. So if I know the distance to one, I can calculate the distance to the other. So in this case, I can figure out that the distance to R2 would be 2.7 times the distance to R1 in a case like this, where their apparent relative brightness was differing by 7.5 times. So we put that in here, their apparent brightness difference in this equation. So again, I don't expect you to calculate it, but I want you to have some idea of how that works. Okay, the second method is very important. It's one of the most important methods we use, called the Cepheid variable method. And again, I talked about these a little bit yesterday. I touched on them. These are stars of variable brightness, and the period tells us what their intrinsic luminosities are. And this was first figured out all the way back in 1912 by one of those computer ladies at Harvard College Observatory, Henrietta Leavitt. She was a productive woman. So again, the longer the period between the peaks in their luminosity, the more intrinsically luminous that star is. So this is what it looks like. Here you have brightness peaks every 50 days, and I can figure out from that period what that star's intrinsic luminosity is at the peak moments. This can be used to determine their intrinsic luminosity to within about 10%. This is astronomy. You can determine anything that's far away to within 10%. That's pretty good as far as things go. And again, once I know that object's intrinsic luminosity, I can figure out exactly what its distance is from this inverse square law formula. So they're really, really great standard candles. So again, here's just a plot. This is from your book showing you the period in days for different kinds of Cepheid variables and what their intrinsic luminosities are. So the fit is not super tight, but it's pretty good. And this scatter amounts to that 10% accuracy I was talking about before. And they can calibrate these now with parallax measurements to make sure that they're accurate, because that Hipparcos mission I mentioned before, named after that Egyptian astronomer, was used to get distances to several of the Cepheids, and also the Hubble Space Telescope has been used for a few of these also. Okay, let me just mention a little bit about the history. I did say that this Henrietta Leavitt, she was the first to discover this relationship, and she found actually one in the Large Magellanic Cloud, one of our near neighbors. So she knew that this relationship existed, but she didn't know why they pulsated. We know now it's because there's a mismatch in the amount of energy produced in the core versus that gravitational contraction energy. It can't stabilize itself quite well enough to be consistently of the same luminosity. But in essence, that variable luminosity tends to be larger in larger stars and smaller in smaller ones. That's what our observations tell us about these particular objects. That doesn't mean these things are going to be variable their entire lives or anything like that. This is a small fraction of these stars' lives, but nonetheless, if we catch them in this phase, we can use them as distance indicators. Okay, so they can be used to get distances up to about 100,000 light years using the Hubble Space Telescope, and this was one of the primary rationales for launching the Hubble Space Telescope. It was in the original designs for the instrument. It was one of the big arguments that astronomers used to try to get the money to build the Hubble Space Telescope. And as you might imagine, as I showed you earlier, they're really used as a basis for getting even larger distances. Okay, so the third type of standard candle, again, extremely important, are supernovae from white dwarfs, which we talked about before. The reason we can figure out these objects' intrinsic luminosity I talked about yesterday, because there's this 1.4 solar mass Chandrasekhar limit I talked about, and if a white dwarf goes over that because it's captured matter from a nearby star, it will explode. So we know what that limit is. We know how much mass is converted into energy using Albert's equation. So I can figure out what this object's intrinsic luminosity is from just using basic physics. Well, these particular objects, some of them can be up to 10 billion times the luminosity of the sun at their peak. So that's great. That means you can see them from extremely far away. That's why they're really useful. Instead of the Cepheid variables, you can't use them to see that far away. But these, you can see quite well across big chunks of the universe with. You're going to pump out 10 billion times the sun's luminosity. That's like the Milky Way galaxy, essentially. Okay, the only problem with these is they don't go off very often. Once about every 100 years per galaxy. So luckily we have a lot of galaxies in the universe, so we have to look at a lot of them at the same time to try to find them going off. And there are people who, again, spend their whole lives doing this. But we don't have more than a few hundred measurements because of this very reason. We don't have, unfortunately, telescopes monitoring the sky down to super deep depths. It's expensive, and you need a very wide field of view, and we don't usually build telescopes like that. So a lot of that work is done by people looking at small sections of the sky and hoping they see one go off, and they do occasionally. But within the next, 8 to 10 years, there'll be a new telescope built in Chile called the LSST, and that's one of the jobs it's going to do. It's going to look at huge swaths of the sky over and over again. It will map I think, a third of the entire sky every month or something. So it'll be a really good way to find these new white dwarf supernovae. And as they've been used to look back to greater than 10 billion years. Our universe is 14 billion years old. These things can look back to 10 billion years. That's a pretty good distance indicator. Okay, a third method is something called the Tully-Fisher. In this case, it got named after the two chaps that discovered this method, but it's a pretty simple method. There's just a relationship between rotation speed of spiral galaxies and their intrinsic luminosity, the entire luminosity of a galaxy in this case. Now we're not talking about individual stars, we're talking about an entire galaxy. So if they rotate faster, they find that they are, as a whole, more luminous. That, of course, has to depend on mass, because luminosity depends on the number of stars, and of course the number of stars depends on mass, hence rotation speed is related to mass. Pretty simple to figure that out. This is what the relationship would look like. Again, this is kind of idealized, but again, you have rotation speed here and luminosity here. So if you have higher rotation speed, you get more luminous, more luminosity. So you can figure out the intrinsic luminosity of these galaxies and figure out their distances. This has not been done for huge numbers of galaxies because it's very hard to get very good estimates of the rotation rates of spiral galaxies. You can get it for really nearby ones, no problem, but as you get farther and farther away, it gets harder and harder. Okay, the fourth method is something we call Hubble's law. And as I said before, it's not a standard candle method. It basically uses redshifts of objects to determine their distances rather than using intrinsic luminosity. So redshifts of objects. Now I'm talking about Doppler shifts moved into the red. So we'll talk a little bit more about that after I think we take a break. That sounds okay with you. We'll take a 10-minute break.